Welcome back, Physical Science 20. This is the third installment of the booklet 6.3 heat capacity. So we looked at two examples already. We'll look at a third one and then maybe do a few practice questions. So we ended up here. We did number one, in which we figured out the specific heat capacity of an unknown metal. Problem two involved figuring out the mass of the metal, if we knew it was iron in this case. 3 is a little more tricky. It involves looking at either a final temperature or initial temperature. Let's find out. During an investigation, 200 grams of silver is heated to 90 degrees C. The hot silver is then placed into 300 grams of ethyl alcohol that has an initial temperature of 5 degrees C. Determine the final temperature of the silver alcohol mixture. Okay, and we're told the grams of, so we don't have to use densities here. We're told the mass of the ethyl alcohol, which is good. So we know everything here except final temperature of the mixture. So you can see here we know everything. And then substituting everything into the formula here, we don't know T2. So the final temperature that the alcohol silver mixture reaches, we don't know that. So we can take a look here. 0.2 times 2.4 times 10 to the 2 is 48. Over here, 0.3 times 2.46 times 10 to the 3, it gives us 738. And I just leave this as T2 minus 5 and T2 minus 90, respectively. And you can see here, it's just like, really, it's a grade 9 or 10 math question. We're going to do here is distribute this. It's really a monomial times a binomial, so multiply by T2, multiply by negative 90, multiply by T2, multiply by negative 5, and we'll be able to get that. So 48 times T2, 48 T2. 48 times 90, negative 4320. And similarly over here by distributing it. So with that, we can combine all of our, now usually in math you would treat this as X. Here it actually means something. X means a final temperature, so I use the variable T2. So combining like T2 terms, 48 T2 plus 738 T2 gives us 786. And then negative 4320 and negative 3690, negative 8010. Then it becomes a grade 8 question for sure now. Add 810 to each side, and I get that. And then lastly, it's 786 times T2, so I divide each side by 786, divide by 786, and I get a temperature of 10 degrees C. So notice in these questions, the units are put in so you can easily see how things are canceled out. But as I was verbally going through it, I didn't mention those units just to make it a little bit easier. All right, so we could solve for anything in that idea of exchanging of heat. So 2 practice questions. So I'd like you to maybe try these, see if you can try both of them, and I'll post the answers here. So the first one involves looking at final temperature. It's going to be a tricky one like this last one. And then number 2 is the specific heat of the unknown bar. Okay? So maybe pause the video, try those, and then come back and see how you made out. Okay, if you had a chance to do both those questions, here's a summary of what you would have found in question number 1. So we know the mass of the metal, specific heat of the metal, T2 minus T1. We don't know T2, so we have to leave it as T2 minus 100. The alcohol, 1.5 kilograms. The specific heat capacity of alcohol, we'll look that up on the table, 2.46 times 10 to the 3. And again, we don't know T2, so we have to leave it like that. So all of that, you should be able to pull from the question here. So 2 grams of aluminum, I know it's aluminum, so we look it up on the table. Ethyl alcohol, 1.5 grams. So we look that up on the table, we get the specific heats. So you have every piece of information you need there. So Q metal plus the Q of the alcohol. Thermal energy and thermal energy equals 0. MC delta T plus MC delta T equals 0. And again, using subscripts to distinguish between both items. And then just simply substituting everything in. So 2 kilograms, 9.2 times 10 to the 2. T2 minus 100. My alcohol, 1.5 kgs, 2.46 times 10 to the 3. Temperature change, T2 minus 18. I kind of ran out of room here, so that all, of course, equals 0. Multiplying these two out, kilograms cancel, I'm left with this. Kilograms cancel, I'm left with this. And then, of course, we distribute 1840 times T2, 1840 times negative 100. 3690 times T2, 3690 times negative 18, and I get that. Then again, combine like terms. So combining all the T2s, 1840 and 3690, I get 5530, negative 184,000, and negative 420,000. I get that. Add 250420 to each side. And I get this. And then again, divide by 5530. And I get the final temperature, hopefully, 45.2839 degrees C, but just rounding that off to be 45. Okay, so very similar to the one we did in the example. The next one I think I mentioned was finding specific heat. So writing down all the information we know here for the second one, this is what you should have got. The mass of the metal is 4 kilograms. It was at 100 degrees C, transferred thermal energy to water, so it ended up at 35, so final minus initial, negative 65. The water was 500 mils, which is 500 Gs, which is 0.5000 kgs. Specific heat of liquid water, 4.18 times 10 to the 3. And yes, the water reached the same final temperature, 35. It was originally at 20, so that's 15. So again, I pulled that all from this question right here, gang. So substituting everything in and multiplying it out. So Qm plus Qw equals 0, or MC delta T plus MC delta T equals 0. Substituting this all in, we get that. 4 times negative 65, negative 260. 0.5 times 4.18 times 10 to the 3 times 15, I get that. So to isolate Cm, I need to first isolate negative 260 times Cm. So of course this is add, so I need to subtract from each side. The simple math manipulation, equation solving at pretty much a grade 9 or grade 10 level. So 260 times Cm equals negative 31,350. So now divide by negative 260 each side. I get this, 1.2057 times 10 to the 2, and I went with 2 sig figs here because one of my numbers was 2 sig figs. See the mass of the metal there? So I get 1.2 times 10 to the 2 joules per kilogram degree C, 120. Okay, so those are the questions there, folks, the practice questions. If you look at the last part of this booklet, thermal energy, expansion and contraction. Of course, living in Regina, Saskatchewan, we have a lot of expansion in the summer, a lot of contraction in the winter, and it plays havoc with our roads, making potholes. Really difficult to keep up with all of that movement. So as a substance absorbs thermal energy, some energy is transferred into kinetic energy, so the particles spread out and increase in volume. The increase in the volume of an object due to its increase in temperature is expansion. An understanding of thermal expansion is important to civil engineers who design various types of structures. For example, metal-framed windows require rubber spacers to account for any changes in size caused by temperature changes. So it depends where you live on the planet. All of these things need to be considered, expansions and contractions during seasonal changes. So special bridges require special joints called expansion joints to prevent pressure from bending the metal components of the bridge on hot summer days, as you see over here. I think we have a few in Regina that are like this, actually. So you can see here, here's a regular road, here's a bridge, and you can see these finger-like projections here. They expand so they can fill in the gap, or contract and still fill in the gap, but not as much. So it allows movement there. Sidewalks, of course, come in blocks like this with a little joint in here so that expansion is allowed to happen and contraction. If it was just one big long piece of cement, just take a look at your driveway and see what happens there. A lot of cracking is involved. All right, so if we look back here, where am I? Here I am. where am I here? So, and of course, concrete, so I want spaces between the slabs to make room for expansions as temperatures rise. Too far ahead. Likewise, when the substance cools down, their particles release kinetic energy to the surroundings and decrease in volume, or the amount of space taking up, resulting in thermal contraction. All substances that expand in warmer weather contract in colder weather, so of course you have to keep that in mind. All right, that's it. That's the end of 6.2. So highlights: specific heat capacity, the amount of heat needed to raise the temperature of 1 kg by 1 degree C. Of course, we have this relationship that we use, Q is equal to MC delta T, when something is heated up or cooled down. And then, of course, what we looked at here recently is the principle of heat exchange, where thermal energy goes from a warmer object to a cooler one. You can use the idea that thermal energy released is equal to thermal energy absorbed. Therefore, the net result is zero. And, of course, this last part, thermal expansion and contraction. All right, so I think you've done 1 to 5 already. 5 was kind of a tricky one, in which you had to determine the final temperature. So that just leaves 6, 7, 8, 9. We won't have to worry about 10. So 6, 7, 8, 9 involve this idea of the principle of heat exchange. Some hints here. Water, 3 liters of water is equivalent to 3 kilograms because of the density being 1 gram per milliliter. And again here, 400 mils of water, that's 400 grams, which is 0.4000 kgs. Okay, so go ahead, work on those questions, and we'll see you again.